Hello, and welcome to our new Unit 2. And we're going to be opening up the world of functions outside of the linear world. In Unit 1, so just a quick review, we talked about a lot of things function related. What is a function? What constitutes it? What the domain and range are? What a piecewise function is, operations with functions, and composite functions. And for the most part, we stuck to lines. Y is equal to mx plus b was our foundation for this, and we know how to graph linear functions, linear equations. Whether it's horizontal, whether it has a slope that's positive or negative, and whether we have a vertical shift that's shifted around on the y-axis, and how we have y-intercept changes. And we are now opening up that world to quadratics, to roots, absolute value, cubics, third roots. So all of this is going to open up, okay? And we are going to identify what a parent function is. So if you think of a parent function is the simplest form of a family of functions. So for instance, y is equal to mx plus b represents most linear, how we represent most lines in the xy plane. But the most basic form of this, if we have, for instance, 2x plus 2, we know that there's a shift of 2 up and a rise of run of 2. So it should look something like this. But this is not the most basic form of it. The most simplest form of a y is equal to mx plus b is actually just y is equal to x. Sorry, anything in pink you don't have to copy down if you don't already know that. Y is equal to x. It's the most basic form. It means your slope is 1, your y-intercept is 0, and it looks just like this. This is the parent function for all linear functions. All linear equations. So a parent function for instance, x, anything cubic is x squared. It is, and we're going to fill in this definition right now. It is the simplest form of a family of functions. Simply put, no pun intended. Simplest form of a family of functions. Okay? And what's nice about this is that you could actually graph this using your graphing calculator. It's very straightforward. If you have one, I would highly recommend taking it out because I'm going to show you how to access the entire table of values using your graphing calculator, and it'll be very easy. So if you're starting in your answer or your home screen of a TI-83 or TI-84, hit the y equals button in the top left, and then hit x, and then hit the squared button. And there it is, x squared, and then hit graph in the top right corner. And you get this graph, a parabola. And that should happen. You could always, for mine, you could always zoom in. You could see all the values. And you could see that it goes through the origin at 0, 0. And that's what should happen for all of these parent functions. As long, for the most part, it will go through 0, 0. And hold on, let me switch this out. So 0, 0. If we want to, we could actually just plot the points and do them algebraically. For instance, 1 squared, if I plug in a 1 here, 1 squared is 1. 2 squared is 4. 3 squared is 9. And ironically enough, that process repeats. Negative 1 squared, remember, is negative 1 squared. So negative times a negative is a positive, and that's why we're shooting up in this direction. Okay? Negative 2 squared is 4. Negative 3 quantity squared, sorry, I was about to write negative 3. Negative 3 quantity squared is 9, and that's why we have that in the left direction. It is also moving upwards. You could also see this on your graphing calculator. So you see in the top right corner, right above the graph button, it says table. You could actually hit, since it's in blue, you could hit the second button and then hit graph. And then you could see actually all of the table of values. And I'm going to keep it in this window starting at negative 3. We see it's 9, 4, 1, all the y values, 0, 1, 4, and then I could scroll to 9. So you could actually see all this also on your graphing calculator. So if we actually do this here, 0, 0, 1, and then 2, 4, 3, 9, which is off of our graph it looks like. So 1 to the left. Oops. And we get our parabola. Make sure you put arrows at the ends to imply that it's going on forever. So our x-intercept is going to be 0, 0, as is our y-intercept. Domain. Well, let me rephrase it. This is the coordinate, but the y-intercept is actually just 0. Same thing for the x-intercept. Domain. All the x values that exist. Since we could plug in any x value and square it, it goes on infinitely to the left and infinitely to the right. So our domain goes from negative infinity to infinity. Parentheses for infinities. Range, however, remember I said it's a scan from bottom to top. Notice that none of the negatives actually fill in. Remember, anything in pink you don't copy down. Our y values actually start at 0. So the moment we hit the x-axis, or the x-axis, we start getting points, and it goes up infinitely beyond our graph because the arrows imply that. So we could say our range starts at 0, including it, and it goes to positive infinity. And then we also see some symmetry here. If I drew a vertical line straight down the y-axis, we could see that it mirrors itself like a book. So we could say our symmetry is about meaning like at that point, the y-axis. And voila, there's our parent function for quadratics, the most basic or simplest form of the quadratic family. So, moving forward, we need to know what all of these will look like, and then build our graphs from there when we actually do transformations of them. Like if I had to vertically shift this up 3 units, then it would look like this. Okay? Or if I had to shift it to the right, it would look like that. So we are eventually going to do transformations like that. And we're going to eventually stretch and compress these. So you'll see what that is in a later lesson. So we also have square roots. Square roots are a little tricky. Notice that we start at 0 because can you ever take the negative of a square root? Nope, that is impossible. You could go into the imaginary numbers realm and that doesn't work, at least not yet. So we start at 0. And once again, if we wanted to, we could throw this into a graphing calculator, but we could just do these by hand. Square root of 1 is 1. Square root of 4 is 2. Square root of 3 is 9. Square root of 25, notice that this is, we skip 16, is 5. So we could actually graph these by hand because we have an x and we have a y. So 0, 0, 1, 1, 2, 4, 4, comma 2. So 4 to the right, 2 up. And then 9 is off of our table because it's 1, 2, 3, 4, 5, 6, 7, 8. So we should have something that kind of looks like this. Okay, just to show you that this works here as well. I'm going to go to y equals and clear this one out because we don't need that anymore. Square root is the same as a square button, but with the second function. Put x inside the underneath the radical, hit graph, and we get that exact graph. You compare them, and it looks just like it. Okay? Square roots. Absolute value follows the same logic. You can put any negative number in for x, and it will still work. So, let's see what we got. If I do absolute value of 3, remember this absolute value is the distance away from 0. How far is negative 3 from 0? 3. It's always going to be a positive. Negative 2 is 2 units away. Negative 1 is 1 unit away. 0 is exactly at 0. 1 is 1 unit away from 0. And we have this pattern. Negative 3, 3. 3, 3. Negative 2, 2. Negative 1, 1. 0, 0. 1, 1, 2, 2, and 3, 3. And it should look like a V. So all absolute values will resemble a V or an upside down V at some point. And if you want to, we could say, oh, I forgot to do these. We'll go back and do that really quick. So clear this out. And we could do absolute value using the math function. And where did it go? It might not. There it is. Absolute value, enter. Hit X, and then hit graph. And you get your absolute value graph. Okay? So, really quickly, x-intercept for the previous one that we forgot to do, 0, 0. Y-intercept, 0, 0. Or if you want to do just x-intercept is 0. Y-intercept is 0. I like to give the point. Domain. Domain is a scan from left to right. Notice that there's nothing in the negative x realm. It starts at 0. This is where we actually get values, and it goes on infinitely to the right. So our domain starts at 0, including it, and it goes to infinity, positive infinity, parentheses. Our range, scanning from bottom to top. Oops, there's my highlighter. Nothing in the negative realm, starts at 0, but then this, even though this is going slowly, it is still moving upwards. So this is going to go from 0 to infinity as well. Is there any symmetry? No, there is no symmetry here, so we write none. We just need to know it goes up and to the right at a slow rate. For our absolute value, x-intercept, we see that it is 0, 0. Our y-intercept is also 0, 0. The domain, since it goes on infinitely to the left and infinitely to the right, it is from infinity, negative infinity to infinity. Our range, scan upwards. Nothing in the negatives. It starts at 0, goes upwards towards infinity. So the range is 0, including to positive infinity. And then symmetry, just like the parabola, it is about the y-axis. Means it opens like a book. Anything that there is on the left corresponds to one on the right, and vice versa. Okay? In this particular case, you could also say it's about the vertex. But for now, we could just say y-axis because it's just the parent function. You'll see what I mean when we talk about when we actually shift things around. Cubics. So if I plug in a -3 here, remember this is -3 times -3 times -3. 3 negatives multiplied make another negative. This is -27. -2 times -2 times -2 is a -8. -1 times -1 times -1 is a -1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. And 3 cubed is 27. We see some symmetry here in terms of numbers. But when we actually graph this, we're going to get something kind of interesting. So graph this, clear this out. X, throw in a cubed. So we have to actually use the up arrow this time and hit 3. And then hit graph. And we get what looks like a parabola that would have went, it almost looks like a parabola, but the left hand of it is actually pointed down instead of up. And that's what happens with cubics. We actually get one side of it points up and the other side points down at the vertex. There's a change in direction. So we have 0, 0, 1, 1, 2, 8, and it shoots way off of our graph. And we get a graph that kind of looks like this. Make sure you put the arrows on the end. And we have an infinite amount of x values to the left and to the right. Our x-intercept is 0, 0. Our y-intercept is also 0, 0. Our domain, like I just said, all the numbers to the left work because we can plug in any negative number or positive number in for x and we'll shoot it and we'll have an output. So this goes from negative infinity to infinity. Our range also, if we scan upwards from the bottom, we have negative values all the way down and all the way up. So this also goes from negative infinity to positive infinity. And we have symmetry, and it's a little strange to say, but this one we're going to have it about the origin or about the vertex. And if I, for instance, cut it from left to right, I could rotate this, and it will be symmetrical. So there is some symmetry here. And you could say it's about the origin. Okay? Excuse me. And last but not least, a third root. What is the third root going to look like? So let's actually graph this one first, just because this one's a little bit strange. I'm going to clear this out. Third root, we actually have to use the math function. And then the line 4, it says the third root. We drop in an x inside of that and hit graph. And it kind of looks like this cubic, except now it's turned sideways. So this is why we chose these values specifically, because the third root of 27 is what number times itself 3 times is equal to negative 27. Well, that's negative 3. Negative 3 times negative 3 times negative 3 is equal to negative 27. For negative 8, it's negative 2. And if you notice, these are kind of inverted. Negative 1, 0, 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. So we actually get this inverted graph of our cube. 0, 0, 1, 1. I'm sorry, 8. I'm sorry. X is 1. Yeah, 1, 1. And then 8, comma 2. 1, 1. And then negative 8. And we get this kind of graph. So this is our parent function for cube roots. X-intercept, 0, 0. Y-intercept, 0, 0. Domain, all the x values work. Scanning from left to right, all the x values have an output. So this goes from negative infinity to infinity. Our range, even though it looks like it's flattening out, it eventually it does go lower and higher. So eventually, you can have cube roots that do go as low as it can. So it goes to negative infinity. Negative infinity to infinity. And then there is symmetry about the y-axis as well. Because if would be the negative y-axis, I forget. Or the negative, y is equal to x. About the origin should still be okay. There's symmetry about, I believe this would be better to say y is equal to x. I'll verify this in a second, or probably in class. I think that's a better way to put it. Same thing for this one. I'll double check these. All right, regardless, we now know what they look like. We now know how a table of values can easily be accessed or evaluated. And we need to know what these look like moving forward. So let's just finish these off. Answer these few questions. Compare and contrast the graphs above. Do any of the graphs look like each other? And how do each equation relate to, how do the equations relate to each other for graphs that are similar? So we're going to answer these questions. What are the similarities and differences between the domain and range and the x-intercepts and y-intercepts? What points do all the graphs have in common? And then we'll talk about graphing these relatively quickly. The method for parent functions. Ideally, graphing 3 points, as you see here, is going to be the easy way around. You're going to want to find the vertex of it, and we'll go from there. But for now, know these, get these down, and you should be able to navigate your homework and moving forward. Other than that, have a good one, and I will see you in the next one. Bye.